You can unmute yourself and now mute again.
Thousands, but it's no worries. You don't have to start again. I just missed it. So, yes. Let me, hopefully, something still works. Yes, a little quiz before I start. What have I plotted here? Here's out the y-axis. Else. This is not number. This is stellar mass on the y-axis. Lifetime. Lifetime is the. So it would be a very logical thing because a very massive star lives about 2.5 million years. So if you start with a 1,000 solar mass star, you might end up 2.5 million years. Very low mass, but it's not. It's actually it's not actually. It doesn't go up to 30, but actually only goes up to 26. That's 26. That's the alphabet. So if your name starts with early letters in the alphabet, like A or B, and you work in the early universe, you can claim stars up to 1,000 solar masses. But if your name only starts with a C, and you work in the local universe, then you have 300 solar masses. This is the most massive star locally, we know, it's 300 solar masses. And that is still a factor 2 higher than the previous one, Feiger et al., 150. You often hear that the IMF is at about 150. That comes from this work. Now, my name only starts late in the alphabet, so I didn't have much. But I have the highest mass loss rate. If I look at my mass loss rate, it doesn't really matter that you start here, here, or there. You end up with nothing. You basically evaporate your stars. So that is why it doesn't really matter. So, and really, this is basically the point of my talk is actually that no matter where you start, you need to understand how much you lose to know where you end up, with what kind of black holes you end up. So that's sort of the basic bottom line. If we observe stars that are very massive today, 100, 150, 200, 300 solar masses, at, say, 1-2 million years, and we observe them, it's very hard to trace back if we started with 200, 400, 600, etc. They basically all converge to a certain point. And that is because the mass loss rate of more massive stars is higher. So they all come back to the same value. Yeah? And the point is, I don't call this the upper mass limit, or physics with the upper mass limit, the effective upper mass limit, because when extra-galactic people want to do population synthesis, they often start with a 0H main sequence mass and a 0H main sequence upper mass. But you might never get there, because during the formation of the star, you should already have these winds. These winds don't suddenly switch on at time equals 0. The atmosphere of the star does not know when the core decides I'm hot enough to start hydrogen burning. These things should be going into one another, and at 10 or 20 solar masses, this might still be detached. You could say, I have a certain pre-main sequence phase, and now I have a certain post-main sequence phase. But if you go up in mass, you have these very high mass loss rates, that starts to play a role in the star formation process. So the actual upper mass limit will be affected by stellar mass loss, not just at time equals 0, but before that. So I'll come to that. And why are these very massive stars so interesting? Well, because of the early universe. So we had a Big Bang 13.5 billion years ago. The universe expanded and expanded, got colder. The first stars formed after a couple of 100 million years. Exact number doesn't really matter for this purpose. Today we're looking here at the high metallicity galaxy, like the Milky Way, and we're looking back in time, and more obvious what is happening there. Yeah, we have JWST observations of redshift 10, but these are the integrated light of populations, but there are also individual features like gamma ray bursts at redshift 9 that tell us that there were massive stars there probably making black holes at very high redshift. So we know massive stars exist, and there's a lot of theoretical understanding that those stars will be more massive than today. Most stars in our Milky Way are about solar mass, but we have stars of 150 solar masses. If you look at nearby galaxies like the LMC and the SMC, over here, we have some glimpses of what happens at low metallicity. Perhaps the masses are higher, but we can test all that because, and I will talk about that in a moment, what we can test observationally nearby and what we can, ideally what we want to do is make predictions for the stars here and then exactly predict what happens that way. But we will have to work in both directions. But my point is that H goes that way, and on average, metallicity will go that way. And it's the metallicity that drives a lot of the cycles of what is happening in next generations. Then there's the issue of, do population 3 stars actually exist? One of the claims was from papers like this, that there are these narrow helium-2 lines, that ultraviolet 1640 helium-2, they're very narrow, yeah. That is usually interpreted, if you see narrow helium-2 lines, it's usually interpreted as nebular. But this is not stellar. Broad lines would be attributed to fast winds from more gray stars. Narrow lines usually to nebular emission. But there might be alternatives, and I'll come to that. But so this is not necessarily a sign of population 3 stars. Narrow helium-2, I'll come to that. So I'll talk about the role. I'm already starting to talk about the role of very massive stars. I'll talk a bit about how they form. I don't really work on the numerical modeling of star formation, but I'll discuss it in this context. Evolution of very massive stars. Then the endpoints, black holes as a function of metallicity. Then an observational project to test some of our models against data in the large and small magellanic cloud, where we take optical and UV data together to learn more about the stellar population. And then an outlook for a high redshift. So why are people so interested? Of course, they're very bright. The 300 solar mass brightest star is 10 million times the brightness of the sun. So you can see them out to quite far distances. They produce a lot of mechanical energy, high mass rates, also very fast wind. So the mechanical energy is high. They dominate the mechanical energy in clusters. Ionizing feedback, they often dominate, and they are important for a lot of chemical enrichment. For instance, nitrogen, I'll come to that. Carbon, other elements, very relevant for that as well. So one example is nitrogen crisis. Redshift, this is a galaxy at Z11, where people were very puzzled to see a lot of nitrogen, interpreted as supersolar nitrogen, where you would actually expect 10 times less nitrogen in the sun. So that's seen as a problem. So how do we have any ideas about how this nitrogen crisis could be solved? As I said, final products. This can be tested now not only from electromagnetic radiation, but also from gravitational waves. And this is a PR picture from the first one, where you had a 40 and 30 solar mass star merging, and those were already quite heavy. A lot of people didn't expect 40 or 30 solar mass stars, but I think if you go to low metallicity, that is actually quite normal. So let's take a few steps back. This is the normal kind of Hertzsprung-Russell diagram for upper mass end. When I talk about massive stars, I normally talk about stars about 50 solar masses. When I talk about very massive stars, there are over 100. And here they stop at 120. That's because the stellar models from Geneva at that time only went up to 120. But we now know we have to go up. They didn't. It's not their fault or something. It's just people didn't want to consider them. And we'll come to that. Why am I showing this? Well, we don't know anything about the evolution of these stars. Stars at 20 solar masses, we know, although there are uncertainties, 20 solar masses, there's uncertainty about the mixing inside the stars. The mixing between the core and the envelope is still unconstrained. There's rotational mixing, there's binarity, there are lots of physical aspects. But despite all that, we know the stars will become red supergiants and make type 2p supernova. That's pretty well established. So we know where the main sequence is, kind of. We know where they do their helium burning, and we know their end product. They make probably neutron stars, not black holes. I would say that above 20, so this whole part, we know nothing. It is still very, very uncertain. We don't even know if a star goes that way or that way. If you have rapid rotation, You might have a 40 solar mass star that doesn't do a classical evolution, but a chemically homogeneous evolution, and make classical Wolf-Rayet stars that way. Yeah? There are other evolutionary scenarios where stars do a more classical scenario, then hit the Eddington limit, but they lose a lot of mass, become very unstable, might get rid of their hydrogen envelope, and that way might make classical Wolf-Rayet stars. We don't know if classical Wolf-Rayet stars go supernova or not. We don't know where all the other supernova type 1b's come from. Do they come from Wolf-Rayet stars or only a subpopulation? Do they come from lower mass binaries? Because another way to get rid of the hydrogen envelope would be that when you have a relatively close binary, you remove the hydrogen envelope in the binary interaction, but then you should see lots of strict stars below the Wolf-Rayet stars, and we don't see those. At least not in the numbers expected. So there's a lot of questions. So with you would think with all the questions that you have at 20 solar mass stars, they're even worse here. But there's also lots of opportunities, because if you go up in mass, the wind becomes more and more important, and at some point, at about 100, the stars now such large convective cores that very quickly the star is basically very simple. It's chemically homogeneous, and at that point, it's only one parameter that decides the evolution of the star. So in different mass ranges, different physical effects will determine the evolution of the star. Once you get to very high values, it's not even the mass anymore, it's the mass of rate. That's the dominant factor setting the evolution of the star. So, how massive is the most massive star? That number is just a number, right? What about the physics? Theoretically, we have to consider two accelerations. The radiative acceleration, which is the flux divided by the C, forget about that, it's just a number. The opacity. Opacity times the flux, that's what we are after. Flux you can write as L over 4 pi r squared. That you have to balance against gravity. Both have a nice r, 1 over r squared, so they cancel each other if you think in terms of the Eddington parameter. So the Eddington parameter gives you the ratio of the radiative acceleration of gravity, and these are just numbers. All that matters is the L over m ratio, luminosity to mass, times some innocent looking kappa. Now that's a very innocent looking number, and maybe in undergraduate lectures people have given you that the most massive star is about 100 solar masses, because if you put in something like electron scattering opacity, then you find that the most massive star is about 100 solar masses. The problem is that the opacity isn't just electron scattering, and that the opacity isn't the same in every position in your atmosphere or even in your star itself. So the structure of the star and the atmosphere, the opacity will continuously change. And roughly speaking, when people do massive star formation, they consider the dust opacity. But what is often forgotten is that when that is at large distance from the star, that is the main source. But if you get close to the star, and especially very massive stars, you get overlying opacity from winds. And that is the one that I think sets the upper mass limit. So when we look at the dust opacity and the problems surrounding that, up to about 15 years ago, people found it very hard to make any stars over 15, 20 solar masses. So basically, for a long time, there was a radiation pressure problem that to make a star more massive than 20, the radiation pressure could not overcome the gravity. And the only way to make stars more massive than 20, and there were 50 solar mass stars. So how do you do that? Was to merge. 20 plus 20 is 40, 40 plus 40 is 80. That was the only way. Until they started to do 2D and 3D calculations, and they found that the matter can sneak in by the equator. There's a lot of radiation escapes over the poles. So that way, basically, it's shielded, the material is shielded from all the radiation, and you can still build a more and more massive star. And that in the simulations, they could maybe make 50, 60, 70 solar mass stars, no problem. And if you would start with even more, there's no fundamental physics limiting that. As far as I know, it's unlimited. So you could make 1,000 solar mass stars as well. So that doesn't set the upper mass limit. Okay, what about observations? If you want to find the biggest star, you go to the biggest cluster. If you want to find a big fish, you don't look in a small pond. You look at a big ocean. So that's the biggest local star-forming region, R136, in the center of the Transitional Nebula of the LMC. And that is where you have this R136 cluster. It's a 10 to the 5 solar mass cluster. And it once was thought that this was a supermassive star of 3,000 solar masses. But then people did higher and higher spatial resolution, and they found it broke up in A1, A2, A3, and a couple of other ones. So at this point, when I talk about 300 solar mass stars, that's the star for the mass for A1, people say, aha, once was a claim for a 3,000 solar mass star, that broke up in all these little constituents. They're now only 300, wait another 10 years, better high spectral resolution, spatial resolution, and they will break up in 10, 30 solar mass stars. And I say, no, that's not going to happen because physically they're totally different. And we know that because the spectra are totally different. A 30 solar mass O star has an absorption line spectrum, whereas these stars have very strong emission lines. And that means the physics is totally different, the spectral imprint is totally different. I'm not saying that A1 may not have a tiny little binary that contributes a little bit to the light, and that the mass comes down from 300 to 290, but the fundamental point that the 150 solar mass limit is way higher than that. I don't see any way out of that. And I'll come to that. If you look at the integrated light, so now you add up all the light from all the stars, flux as a wavelength. Here we have this 1640 line again. I'm going to pay some attention to that in a moment. Let's first look at the overall flux levels. There's 7 very massive stars over 100 solar masses. They rival the flux of the 10 times more abundant O star population. This non-VMS are 63 O stars. They have basically the same flux. Yeah? So if you're just interested in the flux, the very massive stars and the O stars are equally important. Yeah? But the O stars, if you now look at the helium-2, this huge helium-2 line, the O stars make none of it. The 7 very massive stars make all of it. So if you want to understand the helium-2 emission, you need to look at the very massive stars. And the reason is that these winds are fundamentally different. They're optically thick, whereas the O stars all have optically thin winds. So we really need to understand the winds. We need to understand the winds to understand the stellar evolution. We need the winds to understand the physics of the spectra. And we need also the winds to understand the ionizing flux, especially the helium-2 ionizing flux. Because if you have your mass loss rate wrong by a tiny fraction, say 10% or so, either the wind is optically thin or thick, and I'll show that's a huge difference. And that could mean that you get your helium-2 emission wrong, not by a factor of 10 or 100, but like a billion. Either they come through or they don't come through. Yeah. So we need to understand these winds. So the theory was developed 50 years ago by Kastner and Klein, and basically you have the photons, you have your opacity. We include all the elements up to atomic, the periodic table 30. So CNO, silicon, they're all included. Hydrogen, helium, they're all included. But it turns out that iron is the most important line driver, and I'll come to that, why that is. And then the rate of the mass loss that you lose in a typical O star, that's like 10 to the minus 6 solar masses per year, depends on the Z, it's the metallicity, the luminosity of the star. The more photons you have, the higher the mass loss rate, the mass of the star, because the lower the mass, the higher the mass loss rate, because the gravitational potential is easier to overcome for a lower mass star. Or sometimes people say more massive stars have stronger winds. I say no, it's the exact opposite. But the reason is that the L is much higher. You have an LM ratio because the luminosity is so much higher. That's why the mass rates are. But it's really depends individually on all these parameters. And you really need to be aware. You can't just say, oh, I know the mass rate because I won't know one of these parameters. You need to know all of them. And actually maybe even more. But the temperature of the star is very important as well, because the temperature sets the ionization stratification, so it sets the opacity in the wind. And if your opacity changes, then the interaction between the photons and the matter changes. So we make models like that, and this is looking like a simple physical restriction. Your photon is absorbed, is then re-emitted, and it's more or less isotropic, so the initial momentum goes that way, and therefore you get an outflow. But this same photon, you could kick this atom out, and that same photon could potentially use and kick out another atom over there, and then do the same thing over there. And in that way, you can pump up the momentum many times. And actually, if we do that in a multiple scattering Monte Carlo code, then exactly that is what we get. Not quite the hemispheric scattering, but if you take realistic opacities and elements in your atmosphere, then at every point in the atmosphere, you can have radial momentum going outwards, and you can get wind efficiencies m dot v infinity. The mass source rate times the v infinity, so the momentum per second is they could rival the momentum per second from the radiation field. So the efficiency eta is the difference between these two. And this eta efficiency can become much higher than 1. At 1 is the critical point where you go from optically thin to optically thick. You can actually show analytically, write down the equation of motion, that there is a point where the wind optical depth crosses unity exactly at the point where the wind efficiency number crosses unity. And at that point, you get much higher mass loss rates. And we have calculated this. We've now implemented stellar evolution. I'll talk more about the stellar evolution in a moment. If you plot the mass loss rate versus this gamma parameter, so here are the normal O stars at 20, 30, 50 solar masses. Of course, the mass loss rate will increase if you go to higher mass stars, but you actually need to boost them because of this multiple scattering effect. Mass loss rates are much higher. So it is this kind of relation, normal O star relation, that is normally applied in very massive stars in stellar evolution and population synthesis. So severely underestimating the mass loss rates of the most massive stars. When we include this in our MESA models, we get very interesting looking new stellar evolutionary tracks. Normally, a 100 solar mass star does something a bit more traditional, an inflation that goes horizontally. But the evolution of these very massive stars is determined by vertical evolution. So now we have a 500, 400, 300, 200 solar mass star, and all they drop their mass and therefore their luminosity. So they keep dropping in a vertical way up to the same point, and then they will have exactly the same Wolf-Rayet future as well. Where in these classical Wolf-Rayet stars, helium burners, they'd be very hot and also produce a lot of ionizing radiation, helium-2 ionization, for instance. Now, this solves a number of problems, because the problem with any mass loss recipe, if you have mass loss rates that are too low, if you get close to the Eddington limit, the star wants to do this, they want to inflate. And that means if you want to calculate stellar evolution models, you need to solve that problem. And sometimes people do tricks in stellar evolution codes with the super adiabatic mixing, but that's all very approximate. If you have high enough mass loss, you don't get there. So one way to solve this inflation problem is to have mass loss rates that are high enough that you basically go back to your initial position. The problem is if your mass loss rate is too high, you strip the star straight away. So you have a very fine balance in most stellar evolution models, if they are very stable at all. But on the one hand, you don't want to have the mass rate too low, because you inflate like crazy, or too high, and then you strip. Yeah? So even if you could construct a mass loss recipe that's exactly balancing the two, and you might get it right for 100 solar masses, then you're not going to get it right for 101. I forgot to tell you something. All very massive stars have the same temperature. So if you look at R136, all these stars have the same temperature. So how is that possible? They don't have exactly the same mass. So if one had 100 solar mass and the other 101, you could not get them at the same temperature. One should be a red supergiant over there, the other one should be blue. The only way that I can think of that this could be right, that they all have the same temperature, is if you have this vertical evolution, the mass rates are high enough that you basically suppress that inflation that way, and you evolve vertically downwards. And the consequence of that is basically that your stars evaporate. At least in our own galaxy, as I showed earlier, that's the situation. After 1-2 million years, you are severely come down in your mass, even if you started with 1,000 solar masses. And I'm not saying 1,000 solar masses stars exist. I'm just saying, if in the formation process you were going to make a 1,000 solar mass star, it may well be that you interrupted early because of mass loss, and that you only ended up at 600. To me, it doesn't really matter, because it isn't determined by that number here, but it's determined ultimately by that. That will decide what kind of black hole you get, not what happens here. But this might all vary. When? Low metallicity. We know that the low metallicity universe is very different. We see long gamma ray bursts with preference for low metallicity. We have superluminous supernovae in low metallicity galaxies, and we have this funny helium-2 emission that you only see in low metallicity star-forming galaxies. So the fundamental physics underlying all that was almost, I think, is almost certainly this metallicity-dependent winds, and therefore that you get different black holes. At lower metallicity, you can have higher mass stars and higher mass black holes. Can we test that? Well, this is really interesting now, of course, in the last 10 years or so, that there are additional constraints from gravitational waves. Up to that point, people only had electromagnetic Newton stars and black holes. And the black holes, like Cygnus X1, is the most massive black hole in the Milky Way, with 20 solar masses. So there were people claiming that's the maximum stellar black hole you can get, is 20 solar masses, because that's what was found. But then the first gravitational wave occurred, and it was 40 solar masses. So, and now we even have 85 and 66 merging to make an intermediate mass black hole higher than 100 solar masses. So we now know intermediate mass black holes exist. Now the question is, how do you get those? Are these stellar black holes or not? Yeah? And we'll come to that. So we need to know how this metallicity dependence comes in. And that means we need to know how the physics of these winds works. And it depends a lot on how many lines you have. That is what sets the opacity. And of course, the abundance of a given element. So if you have a simple element like hydrogen, we only have a few lines. Whereas if you have a complex atom like iron, this is iron 5, Gaussian diagram, just the number of levels, it's already completely black. If you include all of it, it would be totally black. You have millions of lines. So the fact that hydrogen is so much more abundant, in our galaxy 2,500 times more abundant than iron, this does not drive winds. This does. Iron wins the game compared to hydrogen, even though this is so much more abundant. You can play the same game with carbon. Is carbon important? Because carbon is an element that is created in that same massive star. Massive stars, in their helium burning, you make 3 heliums into a carbon. A carbon is a metal. So when people talk about metallicity, Z, if you make carbon, they include it in Z. But that is not necessarily true, because iron is already present at the very early, there's also initial carbon, but that's really irrelevant. The iron, the initial iron, is potentially very important in driving winds, or the carbon that is made in the stars themselves. So that was the question I asked myself a long time ago now, but it is still relevant today. If these kind of elements, intermediate mass elements, drive the winds, that's self-enrichment, then every host galaxy should have similar physics. Whereas if iron drives the winds, then it's the initial, then it matters whether your Wolf-Rayet star is in the galaxy or the SMC or even lower metallicity galaxy. That becomes very important. So what I found at the time was that the old idea that it was all carbon, because it was included in Z, that if you have mass loss rates versus metallicities, the idea was that it was always the same mass loss rate, because you have Wolf-Rayet stars, you have metals, therefore you have high mass loss rates. But I found that if you go to lower metallicities, already at a tenth or so, the mass loss rate is already dropping by quite a lot. And that has consequences for things like gamma ray bursts and heavy black holes. we have now improved on this. For instance, these hydrodynamical models, these are also non-delta E models, but they're more sophisticated in many ways. Mass loss rates versus what we now like to plot the L over M, because it's really the physics of the Ellington limit that matters. And you can see that all these models may at some point surpass this eta equals 1, this single scattering limit. So you have optically thin winds with lots of helium-2 ionizing radiation, and then at some point you get them become optically thick, and that drops. So we need to work out exactly which stars are optically thin and optically thin. That will teach us a lot about helium-2 ionizing radiation. So to go back to the black holes, this is a plot that I've seen a lot. The maximum black hole mass versus metallicity. And the first gravitational wave, the 40 and the 30. And what I've seen labeled is that people thought there were strong winds, and then there was clumping, and then suddenly there were weaker winds, and that therefore this had anything to do with that problem. And it has nothing to do with that, because basically at solar metallicity, that's 1 here, you can see in these lines are exactly the same. And the reason is that the winds haven't been revised at all. We still think they're strong. And the only reason why that went into that paper is because we did a population synthesis study with Vink a number of years ago. And we studied that we have Wolf-Rayet-dependent mass loss. So basically, if you have old winds that are not, but the Wolf-Rayet star does not depend on metallicity, then you can't get over about 20 solar masses, even at low metallicity, because you still have these very strong Wolf-Rayet mass loss rates taking the mass away. But now, with the newer ones, where you have the scaling of metallicity, solar, nothing changes. With a low metallicity, we have much heavier black holes. So that would explain these first gravitational wave black holes with a metallicity of about 10% solar. It comes directly from those calculations. So there was an even heavier one a couple of years later, 85 solar masses. Now, people I'm not going to argue whether these mergers come from isolated binary evolution or cluster dynamics. I'm just stating that to get these things merged in Hubble time is challenging. So when an 85 solar mass black hole was discovered, people said this was a problem. They said it is above the permeability limit of 50 solar masses. At 50 solar masses, the 50 solar mass black hole would come from a 37 solar mass CO core mass. If you have reached a carbon oxygen core mass of 37, your gamma 1 goes below 4/3. You get unstable, and you get the whole star basically is obliterated, and you have no remnant. So people said that you could not get over 50, but 50 is not a fundamental limit at all. 50 was just the number at the time in the models from in this case Woolsey. But there's a much more fundamental point, and that is this one. That is what sets the physics of this variability. So if you can somehow create a different configuration where you can have a CO core mass of 37, that you can create a big hydrogen envelope, say 50, and potentially you could get an 85 solar mass black hole without solving, violating the so-called impossible 50 solar mass limit. So I'm not saying that this could not be the result of earlier merging, because that is basically what people at the time invoked, most people I think invoked, is okay, 85 is impossible, the 50 solar mass limit, okay, then we must have had an earlier merging. And I'm saying I don't know, because doing that once is already difficult, doing that twice maybe even more difficult. I don't know, I'm not an expert. My question is more fundamental in terms of stellar evolution, is how can you get, is it possible to get an 85 solar mass black hole? Is there, from a single star physical perspective, possible to get a configuration like that. We have a 37 solar mass CO core and a large hydrogen envelope. And there's two important ingredients to do that. One is that your core cannot be too big. If you go to too high mass star, like a 200 solar mass star, you have this huge convective core and you're way over the 37. So you can't do that. Obviously, it has to be higher than 85, otherwise you never get to 85. So you have to be just above 85, but not too far above. And what we find is what you need is something between 90 and 100 initially. Because with mass loss, you will always go down. But not too heavy. So this is within the mass range that you need to be in. And you want to limit the amount of mass loss here. So you want to go to low metallicity. So when we go to about a 10th or 100th, we can keep the mass loss low enough to still have this huge hydrogen envelope. So it is possible to construct a model like that, and we have many models like this, where we have blue supergiants with relatively smallish cores, 37 solar masses, or just below the 37, to not go parent stable. And that is an if, but if you can somehow collapse that core and also have the hydrogen fall on top, and that helps then a blue supergiant. So a red supergiant, it all happens at a much larger radius. So maybe some of the material is lost. But here the radius isn't that big, and you may actually end up with something like an 85 solar mass black hole. So it is possible, I think, to get from a single star an 85 solar mass black hole. And that would nicely explain then the well, two things actually: the peak at 37 and the maximum at 85. Right. And then we can also make a cartoon at this point of the black hole, the maximum black hole mass below Planck stability as a function of metallicity or age of the universe. The old idea was 50. We find it to be at 93. And then, as I said, high metallicity, you only get your Cygnus X1 type black holes at about 20 solar masses. So you have this regime and you have that regime, and there's a transition in between the two regimes. That happens at about a 10th. That number is a bit more uncertain, but it's about between the 10th and the 20th metallicity. Now, so that means that this regime makes black holes. Here you get parent stability, so you could still get parent stability supernova, but maybe not as many as before. And of course, then the other question is still what happens up there. I mean, I'm not excluding that there could be heavier black holes, even stellar black holes, above parent stability. That is possible, but that is not yet investigated. Right. That is how we can get to the maximum black hole. And ironically, I think it's easier to put firm constraints on the maximum black holes than on the distribution below it. Because the distribution below it, we have all the uncertain physics of mass loss rates, wind properties, stellar properties, etc. So if we want to understand the entire population of massive stars, we need to have, I think, a lot of input from observations. So we have mass loss rates, so all these parameters. And if you want to compare your theory to observations, you also need the stellar parameters, because you need to know, I look at that galaxy, at that star, with that mass, and that luminosity, and that's the mass loss rate I need to compare to an observed wind property. And for that, we need to really do large-scale optical and UV analysis. So now we go more observational, and we look at a UV spectrum and an optical spectrum. So in the UV, we have very nice P-Cygni lines that give us information about wind velocities, thousands of kilometers per second. We can get information about things like ion abundances, but we don't get stellar parameters like log G. You would only get in the optical Balmer lines or temperatures. And then also in the optical, you have this H-alpha recombination line that gives us information about mass loss rates. And in the combination between recombination lines and scattering lines, recombination lines go with density squared, scattering lines go with density linearly, we can get hands on the clumping of stellar winds as well. So for that reason, we extended the Ulysses project. Ulysses is a large Hubble Space Telescope project, 1,000 orbits, for the director, for 500 orbits, massive stars and non-massive galaxies. So I'm PI of this optical follow-up with X shooter on the VLT, where we do the same kind of spectral resolution, high signal-to-noise data in the entire wavelength range to really start to pin down all the stellar and limb properties. And that is an ongoing process that hopefully you will hear more about, X shooting Ulysses. So we do a few very low metallicity galaxies, but most of the stars are in the LMC and the SMC. This is about 20% solar, there's a 50% solar. Sometimes people ask, if you want to understand the early universe, should you not have lower than SMC? Of course, it's nice to also look at even lower metallicity, but most of the physics we're studying, such as mass loss rates, do mass loss rates spin down stars, the rotation rates of stars. The big step in all my stellar models that I've ever seen happens not between the galaxy and the LMC, or between the SMC and non-metallicity galaxy. It happens here, between the LMC and the SMC. The LMC is still quite high metallicity, where winds are very dominant and rotation is not. Because the SMC, the winds are much weaker, rotation rates are much higher. So this is the right range to study the physical change from the high redshift universe to the local one. Now these are Hertzsprung-Russell diagrams. You can plot all the hundreds of stars that we're looking at. And these are, of course, pre-Ulysses. So all these stellar parameters, luminosity, temperatures will be improved. These have all been done either with UV data only, with 3 stars, with 1 code, by 1 person, and then 5 stars, only the optical, by another person. So all the analysis has been heterogeneous, but also the data has been very heterogeneous, always small bits. Now we have a uniform data set, UV, optical, everything. So I think we can improve a lot on this, but more importantly on the mass rates. But you can already see that you see a nicely sampled IMF for the large range account in particular. Unfortunately, I think we're extremely lucky that we have the SMC, don't get me wrong. It's nearby, it's low metallicity, we learn a lot from it. It would have been fantastic if there had been a tarantula nebula in the SMC, so that we would have filled that up as well, but we don't have that. But we have it at least in the LMC. So you can understand the transition from normal massive stars to very massive stars. And you can really start to look at spectroscopic transition from what I mentioned, absorption lines to stronger and stronger emission lines that you get around that kink that I showed earlier. So that is what we want to do. And then we also want to understand the winds. Let me come back to the problems I raised in the beginning. The helium-2 emission, when I do high galactic IZ solar metallicity winds, I always get thousands of kilometers per second winds that give you quite broad helium-2 lines. But if I lower the metallicity, then these lines become narrower and narrower. So suddenly thousands of kilometers per second go in the regime of hundreds of kilometers per second. And at some point, we're going to reach the spectral resolution that high redshift people usually use to distinguish narrow lines from broad lines. So my thesis is that it could well be the case that a lot of the so-called narrow helium-2 emission is actually not nebular, but is stellar with slow winds. At least I think it needs to be considered when these analyses are done. And that means also for JWST. So this is in the UV, this is the red spectrum UV. Obviously that goes to much higher wavelengths if you are doing this in the more distant universe. Finally, this nitrogen crisis. I have to say something about that. This is not just a problem for Dutch farmers. This is a problem for all of astrophysics, apparently. So there are a couple of suggestions where all this nitrogen comes from. One seems to be the one that has been mostly discussed is rotating Wolf-Rayet stars. That means that if stars rotate rapidly and then mix very efficiently, that you might get a lot of mixing. And it is possible, but I would say that when I started looking for rotating Wolf-Rayet stars in the SMC and with polarized light, I had hoped to see lots of rotating gray stars and evidence for a very efficient chemical homogeneous evolution, but I didn't find it. So I'm also a bit skeptical about very efficient rotational mixing as a solution to getting chemical homogeneity. There is another suggestion that supermassive stars, Mark is part of that study, so if you have any questions, then ask him. Much less physical tweaking, I would say, because these stars are chemically homogeneous, but there is a question of whether they exist. If we have stars that massive. So I suggested the very massive stars, these stars over a couple of 100 solar masses, also are chemically homogeneous, or at least that's what our models show. And they all give you this very high nitrogen. So if just give one example from our models, is that for a 300 solar mass star, and while the helium grows slowly, the nitrogen shoots up very quickly. So in these models, this is the LNC metallicity, we can get 1 solar mass of nitrogen from one star, one very massive star is needed. So if you want to explain 500 solar masses of nitrogen, then you need 500 of them, and then you can reach that. And that is a number that is more or less in line with some simple estimates. No proof. I would say all options are still on the table. It's hopefully clear which one I prefer. But independent of who is right or wrong, or which models, and maybe it's a combination, who knows. But all these models are very efficient at high metallicity. And the real challenge will be to see how that happens at even lower metallicity. In some cases, like if you also want to understand globular clusters and so on, you have to go to lower metallicity, and that will be a challenge. But we need to understand how things vary with metallicity. So that is really my final slide then. And I hope I told you the massive star evolution is very incomplete. Over 25 solar masses, it will be largely dependent by this uncertain mass loss rate and processes. That's good news for a number of reasons. One is, and I may not have highlighted this enough, but we have this analytical prescription for what happens at the transition. And that means that at the transition, and we have stars at the transition, we know what m dot is. Because m dot is just L over C V infinity. So if we have uncertainties in mass loss rates, and for most stars, normal massive stars, very massive stars have uncertainties, at the transition we don't, because if we measure the luminosity for those stars, then this is just a constant from Einstein, and that is just a number you can measure from UVP Cygni lines. And basically, the uncertainty, systematic uncertainties in min mass loss are suddenly almost non-existent for those stars. So, because of theoretical progress, I think we have some positive news that we can do this now. And we have much larger samples now, where we can do things systematically. We know that the low metallicity universe is different. I suspect the upper mass limit is Z-dependent. Now, this is different from the claims, of course, for the population 3 stars. Population 3 stars, zero metallicity stars, or very low metallicity stars, you could have, the reason why those are thought to be more massive is because you have less cooling. Because the cooling could not take place by CO. In our Milky Way, you have cooling of H2 and CO, and that has many ways of cooling, whereas in the early universe you only had the H2, and therefore people claim you have more massive stars. What I'm saying is, if you have the upper mass limit determined by these winds, then in the Milky Way you will have a sort of number. What that number is, I don't know, but that number, I can't give you a number, but it will be higher at low metallicity. So I think the upper mass limit will be higher at low metallicity. So we could well go up into extremely massive stars. So that's one of the speculations, and we'll have to find evidence for that. And then, yeah, massless low metallicity will be crucial for these high redshift galaxy interpretations of these spectra, and for things like gravitational wave lengths. Yeah, any questions? Please go ahead.
Thank you very much, Jorick. Any questions? Okay.
Ask about the plot you showed. Those start with different initial mass that lose mass and then they all evolve to the same value to the years. This, if I understand, this is for more high metallicity.
Yeah, this is high metallicity. So at high metallicity, I call that the evaporation.
Okay, but then it seems to me you should expect here that when you look at the distribution of masses, these objects in dissolve, you get a bump, right? At around close to 100, because all these objects concentrate in the same place. So is that a prediction of this model?
Yeah, there might actually even be a bump there. There seems to be a bit of an excess there, but I'm now claiming that it almost sounds from maybe the way I described it, of course, that we don't know the difference between 200 and 1,000. I would still expect there to be more stars that want to go here and want to go there. There will still be some sort of IMF effect, where this will be preferred over that. So I suspect that this effect will be subtle. I'm saying if you don't have any more information for one star, you can't tell the difference between that and that, but it's more likely that than that. So I think that's what, yeah.
But Feiger's claim of an upper limit at 150 comes exactly from this point, right?
Yeah.
He sees like a truncation and says, if I see this many stars at 100, you just extrapolate the slope, I would have expected 20 more stars or 10 or something, way more than one, and so therefore this is a fundamental limit, but it might be that they just piled up at this mass. So they were once higher or they never reached that mass because of wind, right? So.
Right, but there is some distribution of power all that, right? And then, so does the mass distribution just look like a cutoff power law, or is there a little bump here? What do you get? Right? Probably the question.
Yeah.
Yeah, we don't have fantastic statistics. That's the question. So yeah.
Valentia?
Yeah, I have a question regarding primordial population 3 stars.
Yeah.
So in principle, we could see them. I guess that it will be very rare, but you may see two black holes merging, which one of them has extremely high mass, and I guess that using theory, one can claim that okay, you can form this black hole mass if your metallicity is below some value. So could you claim from this theoretical argument and there is no way of observations, when you have seen something that must come from a population 3 star, because the black hole is so massive that it cannot be produced by a later generations of stars?
You mean from the gravitational wave?
So you see the merging of the stars, the gravitational waves, and you'll see that at least one of the black holes has to be, I don't know, 300 solar masses, something like this.
But one possibility, of course, is that you have some sort of bimodal sort of population 3 more massive higher metallicity, lower mass. I mean, and we see that. I think most stars in our Milky Way are low mass, right? But what I'm trying to say is that even if you're not in the POC3 regime, but at the top end of the distribution, if you go to lower metallicity, I would expect that number to go up as well. So if we see a very massive black hole merging, I don't think we can really say that's POC3. I think that's also a possibility. And these are
even if the mass is thousands of masses.
yeah, even if it's because I don't think we can exclude the existence of extremely massive or supermassive stars at metallicities of the global cluster metallicity, for instance. I don't think we can exclude that. So I don't think we can immediately jump to the conclusion that's POC3.
Yeah. Questions? Yeah, that's it.
Very nice is survey of places
Yeah.
in the LNC and SMC. Because you see that from the SMC you track the beginning of the bridge between the SMC and the LNC, and more interested in tracing the bridge. Do you have stars that you show the blocks separately, LNC and SMC? Do they that's the stars in your survey connect the SMC with the LMC, or you have a gap?
Oh, you mean in the actual bridge?
In the actual bridge.
Not in this survey, I don't know, but there are UV spectra of stars in the bridge. They do, there are some.
And how faint are they?
I don't know for those stars, but yeah, 15 or so. Varies a bit. Yeah.
Yeah, I mean, the GWC nitrogen enrichment, so those are emission lines corresponding to like ISM gas.
Yeah, that is, yeah.
And then like to create that is like mass loss or?
Yeah, I'm not talking about the
exposure,
direct.
or it's,
Sorry, I'm just looking at the source where the would nitrogen come from. I'm not thinking about where the material ends up in the ISM to create that. I'm just saying what sources.
Right, but I mean, if it's through mass loss, then
Yeah.
like, I mean, part will collapse, right? So it's just like a small portion of that mass, nitrogen rich mass that will get lost and pollute the ISM for you to see those lines.
Yeah, yeah.
So every star will contribute little because there is like little mass loss and no metallicity. Then you need a lot of those stars to contribute.
Those metallists are actually not that low. So that's the funny thing. Actually, it looks like it's more like 10% solar. So it's not that low. So on average, it's the case indeed that metallicity will grow with time. But next to our Milky Way, we have low metallicity SMC. And apparently at redshift 11, we have a galaxy with a metallicity of 10% solar.
And then should we see those nitrogen enrichment and something as well?
Yeah, probably. Well, the SMC itself, as I said, is kind of doesn't have that kind of vigorous star forming region like tarantula to give us 100 solar mass stars. But because of other physical properties like rotational mixing, I would expect that the stars will at least show enhancement of nitrogen. The stars will be nitrogen enhanced. You're asking if you looked at the SMC from far away with JWST, what would it look like? I'm not entirely sure if you would see that or not. You think about that.
Maybe one follow-up
Yeah.
question on this nitrogen. I mean, apparently it's really easy to make nitrogen, right? So you
Yeah.
mentioned a few possibilities,
Yeah.
but there are at least 5 more papers where people say, I can also explain this nitrogen. So what do you think is the prospect to disentangle all these possible nitrogen factories? Is it maybe strong lensing, looking at spatial distribution of the gas, or what can we do to learn more about where this comes from?
Yeah, I think solving one problem. I mean, obviously, I think nitrogen price is one problem, but I think it's good to identify the different possibilities, and that's one. But I think you need to simultaneously solve several problems. That will probably give you sort of an answer in the kind of degeneracy of all the possibilities. So, looking also at double clusters, looking at the sodium enhancement, magnesium depletion, aluminium, all that. If that is, then the question is that the same phenomenon? So there will be different questions to be answered, but it will be.
Can JWST see those lines? I'm not.
Which lines?
Can they see other elements that are useful?
They can see argon,
Sodium, aluminium, or magnesium?
No, unfortunately not, but they can see some neon and argon and so on. So there will be some elements that we can learn
Right.
from.
Okay, thanks. Any more questions? Not, I think we've exactly filled the hour, so thank you very much, Jorick, again.